Hello everyone, I'm Oscar Karnalim from University of Newcastle, Australia, and also I am from Maranatha Christian University, Indonesia. On this occasion, I will explain about my research entitled Disguising Code to Help Students Understand Code Similarity. This is a research collaboration with Simon from University of Newcastle, Australia. First is about the background. So plagiarism and collusion are two common ways of breaching academic integrity in programming. One of the prevention strategies is to provide sufficient knowledge about this kind of issue. Like, for example, explaining which practices are allowed and to what extent code similarity is acceptable. Regarding the latter, knowledge about acceptable code similarity. It is basically saying that some programs can be essentially identical despite looking quite different, and that is unacceptable on most occasions. So basically it is simple, but this kind of information is typically explained to students just once, and usually briefly, in a lecture that focuses mainly on substantive aspects of the course materials. As a result, some students will fail to make the connection between this information and their own specific work. One of the solutions is Code Similarity Disguiser, or CSD. It is basically a tool to apply semantic-preserving code disguises to student programs. And with this kind of tool, students can independently learn about the many ways that the program can be changed without affecting the underlying code similarity. Some of you might ask, what are the differences between CSD and existing code obfuscation tools? First of all, CSD ensures that the transformation is natural and realistic. So the disguises are based on reasonably common differences among student programs. Second, unlike other code obfuscation tools, CSD can be safely distributed to students. Why? Because the transformations are nullified by many similarity detection tools. In other words, CSD cannot be misused to trick those tools. There are three other potential uses of CSD. First is to individualize code tracing assessments. So a single piece of code can be transformed with random disguises into multiple equivalent pieces for distribution to students. We can also use this tool to anonymize identifying information in student programs, because a few of the disguises anonymize accessing information, and this might be useful if the programs are to be made public as a dataset. And the last thing is to generate datasets for the evaluation of code similarity detection that incorporate features of programming style. Because most of the disguises are related to programming style. CSD has several characteristics. First, it works with Java and Python, two of the most common languages for introducing programming in Australasia and UK. Second, it has 60 similarity disguises. You can see the paper for details. It has 27 for comments, 8 for white space, 10 for identifier, 2 for data type, and 13 for consent. It can be applied either specifically or in random combinations. CSD has a diagnosing mode that determines all disguises that can apply to a particular program. CSD, the complete documentation and the code are available at my GitHub page, so you can use it directly for your teaching environment. You can also modify the code in case you want to maybe add more programming languages or maybe add more disguises. For evaluation, we have two kinds of evaluation. The first one is preliminary evaluation, which is technical, and it has been completed. Second is about pedagogic evaluation, which is still ongoing. Hopefully, we can get the result at the end of this semester, and we can get the published version maybe at the middle of next year. First, about technical evaluation. So it has two research questions. First, which disguises are the least applicable to student code? Students might see no effect when applying them. And second is about which disguises have the greatest disguising coverage in student code. They might change the code too dramatically, and lecturers might want to advise their students to avoid both of these sets of disguises because the transformations might be confusing, especially for novices. We have three datasets. First, Python student dataset. It has 262 code files from an offering of introductory programming that uses Python and Jest. Second, we have Java student dataset. It has 1,028 code files from various offerings of introductory programming that uses Java. And third, we have Java book dataset. It has 200 code files from an algorithm book. Addressing first research question, applicability. So applicability of these guys is the proportion of code files in a dataset which the disguise is applicable. So it was counted by modifying the diagnostic mode. And the least applicable disguise is replacing words representing mathematical operators with their corresponding symbols in string literals. So basically, plus as a word is replaced with plus as a sign. Why? Because usually we use the latter. We use plus as a sign, not as a word. We have four other least applicable disguises. Double the tabs and replace each tab with two spaces are rare in two datasets. For Python dataset, just automatically convert tabs to spaces. And for Java book dataset, the book authors consistently use spaces for indentation. The last other two are replace conjunction symbol with their corresponding words in both comments and string literals. So for example, like and as a symbol is replaced with and as a word. Why this is rare? Because usually we use the letter again. We use and as a word instead of as a symbol. Many of the least applicable disguises have complementary disguises that could be used in preference. So in other words, students might still understand the impact of the disguises. But still, lecturers might need to explain about the type modifications because one of two such disguises appears among the least applicable disguises and they are only applicable in Java. Second research question is about the coverage. So coverage of a disguise is measured by comparing all code files before and after applying the disguises and averaging the results. So each code file was converted to a token string with all adjacent white spaces considered as a single token. The token string were then compared with running Kaprawin greedy string tiling. Following the equation below, we can get the coverage as a percentage. And there are three disguises with the greatest coverage: double the spaces, capitalized identifier names, and anonymized identifier names. What are the reasons? First, spaces were more common than tabs for indentation in the Python student dataset and Java book dataset. Second, the code files include many identifiers whose names are seldom entirely in uppercase. Pedagogy evaluation is about future work actually, and it is ongoing. So the tool has been integrated to a submission system, and each time a student submit their code, they'll be shown a version of the code with some disguises applied along with a related explanation. So this is expected to motivate further use of the tool while educating students about the futility of trying to copy and disguise code. As the conclusion, first, we propose CSD, a tool to educate students about code similarity for academic integrity in programming. And for classroom use, lecturers might need to explain data type modification, as those disguises might not be applicable to student code. To avoid confusion, students are advised not to start with disguises that result in large coverage, like double the spaces, capitalized identifier names, and anonymized identifier names. Thank you.